What specific problem does your method aim to solve regarding PRNGs and transformers?
My method aims to investigate whether transformer-based language models can learn to predict outputs from pseudo-random number generators, PRNGs, specifically focusing on linear congruential generators, LCGs. The research addresses the challenge of understanding how these models can identify and learn the underlying mathematical patterns of LCGs, which are designed to produce outputs that appear random, despite being generated by deterministic algorithms. By training transformers to autoregressively predict LCG sequences, we explore the implications of model capacity, data variety, and context length on their learning capabilities. Additionally, we analyze the emergent structures within the model that facilitate this learning, aiming to reverse engineer the algorithms used by the transformers to predict the sequences. Ultimately, this work seeks to clarify the extent to which transformers can generalize their learning to unseen parameters of LCGs and the implications for both transformer architectures and the security of PRNGs.
How does the proposed method or algorithm work? Illustrate it step by step, particularly in the context of predicting outputs of LCG sequences.
The proposed method for predicting outputs of linear congruential generators, LCGs, using transformers involves several key steps. First, the transformer is trained to autoregressively predict the next number in an LCG sequence, where it takes a sequence of numbers as input and outputs the next number in the sequence. The model learns to infer the parameters of the LCG modulus m, multiplier a, and increment c from the context provided by the input sequence. In the case of a fixed modulus fm, the model develops emergent structures that leverage the residual number system, Arn's representation of the inputs, allowing it to simplify the prediction task by focusing on the periodic properties of the binary representation of the numbers. The model utilizes R step iterations to reduce the complexity of predicting higher bits based on the lower bits, effectively copying unchanged bits and simplifying the prediction of higher bits. For the unseen modulus case, the model must adapt to different moduli it has not encountered during training. It achieves this by employing specialized attention heads that group numbers, according to their remainders modulo various prime factors, allowing the model to construct RNS representations tailored to the specific modulus being tested. This head specialization is crucial for the model's performance, as it enables the model to estimate the modulus and apply the appropriate representation for accurate predictions.
Can you provide a simple yet illustrative example to explain how your proposed algorithm predicts a number in an LCG sequence?
To predict a number in a linear congruential generator, LCG sequence, the transformer model utilizes a systematic approach based on the properties of the LCG. For instance, consider an LCG with modulus m equals 2048 and a sequence generated by the parameters a and c. The model first identifies the binary representation of the numbers in the sequence, where each digit has a fixed period. When predicting the number at position t, the model looks back at the context and applies an R-step iteration where R corresponds to powers of 2 e.g., R equals 2 k. This allows the model to copy the lowest k bits directly from the context and simplify the prediction of higher bits by reducing their periods, thus enhancing accuracy. The model's ability to leverage these periodic structures and the relationships between digits enables it to effectively predict the next number in the sequence.
What are the theoretical or practical benefits of using your method compared to traditional approaches for predicting PRNG outputs?
The theoretical benefits of using transformer-based models for predicting PRNG outputs, particularly linear congruential generators, LCGs, include the ability to learn complex patterns and emergent structures from the sequences, which traditional methods may struggle to capture. Our approach leverages in-context learning and chain-of-thought reasoning, allowing the model to generalize effectively to unseen parameters and moduli, as demonstrated in the generalization to unseen modulus tasks. Practically, the use of transformers enables the handling of larger moduli and more complex sequences through systematic scaling analyses, which traditional methods may not accommodate efficiently. Additionally, the interpretability analyses reveal how transformers can discover and utilize representations like the residual number system, RNS, enhancing their predictive capabilities beyond simple statistical methods. Overall, our method provides a robust framework for understanding and predicting PRNG outputs, offering significant advantages in both accuracy and adaptability compared to conventional approaches.
How did you validate or test your method? Can you elaborate on the experimental design and metrics used to evaluate performance?
To validate our method, we employed two distinct paradigms, fixed modulus, FM, and unseen modulus, In the FM paradigm, we generated a training dataset by sampling LCG sequences with a fixed modulus, M, and varying parameters, A and C, while the test dataset consisted of sequences that maximized the period according to the Hull-Doble theorem. For the paradigm, we trained the model on sequences with multiple moduli, ensuring that the test moduli were unseen during training, thus evaluating the model's generalization ability. Performance metrics included test accuracy, which was measured by averaging the accuracies across all sequences generated from the test set, and we tracked accuracies at all positions in the sequence. Additionally, we conducted systematic scaling analyses to understand the effects of model architecture and sequence complexity on performance, revealing insights into the model's learning dynamics and generalization capabilities.
What were the key results achieved with your method, and how do they contribute to the existing literature on transformers and PRNGs?
The key results achieved with our method demonstrate that transformers can effectively learn to predict outputs from linear congruential generators, LCGs, with moduli up to m equals 232, showcasing their ability to generalize across both fixed and unseen moduli. We found that a minimal architecture of just one layer and one attention head suffices for the fixed modulus task, while the unseen modulus task requires a more complex model with at least 3 layers for effective generalization. Our interpretability analyses revealed that transformers develop emergent structures, such as binary and residual number system representations, which facilitate systematic predictions based on the underlying LCG algorithms. Additionally, we observed that the model's performance is sensitive to hyperparameters and context length, with accuracy improving significantly as context increases. These findings contribute to the existing literature by providing insights into the learning mechanisms of transformers in the context of PRNGs, highlighting their capacity to reverse engineer complex algorithms and the implications for both cryptography and machine learning.